interpretation is called the value of the stochastic solution. And now we look at the other side. We're going to look at the gap between TS and wait and see. As we know, under some assumptions, namely that randomness is only on the right hand side, it's actually the best approach. Even if it isn't, we can still look at that gap and try to give it an interpretation. Okay. Let's see. Okay. Indeed, what are we comparing? TS comes with its solution X star, which is obtained under uncertainty about the future. That's to say, we have only probabilistic information, and of course, we use that in terms of the expectation that we use as a criterion, but still, it's under uncertainty about the future. Then again, the alternative model, providing the lower bound, is the wait and see, which does to some extent exactly the opposite. Namely, it assumes full knowledge about the future. Well, all futures. And for each and every one of them, it takes advantage of that knowledge in optimizing. Because it then knows what the future will bring, and you can take the best decision given that initial information. That's why the difference between the two is called the expected value of perfect information. And given the interpretation, that name hopefully makes sense. Because that's exactly what it is. It's the difference between having only probabilistic information versus full information, perfect information. And since we're taking expectations, this is an appropriate name. Similar remark applies, as I made for the other gap. By definition, this expected value of perfect information is non-negative. So if you're looking at the maximization version of the problem, please take care of the sign of that gap. Yeah? Okay. Also here, we can talk about interpretation. Given what it actually stands for, the first interpretation is sort of obvious. It's apparently what we need to pay, the cost, if you will, for not knowing what the future will be. So it's the price for uncertainty. We know the distribution, we use that information, but we are not clairvoyant, we do not have perfect foresight. Another interpretation is slightly more practical, maybe. It also gives a bound on the amount of money we will be willing to spend to learn more about that future. Because this tells us, this EVPI, what we can gain at most by having better information. Yeah, so from an application point of view, it could be a bound on what we're willing to pay for market research if we're modeling some production demand setting. Yeah, so that's also an interpretation. Let me stress again, both the value of the stochastic solution and the EVPI are important measures in applications. So, for example, in a few weeks you'll be working on your case studies, then one of the questions will be calculate both and give an interpretation. And it is important then to not just repeat what is written on the slide here, because that's a very general remark, but try to relate it to the application that you're working on. Give it an interpretation in the context of that problem. Yeah? Okay. So everything we did so far was under the assumption of modeling a fixed recourse, namely that in particular also the cost factor Q is random. But we already argued several times that from an application point of view, it's very natural to also allow randomness for those costs. Usually there are future costs, and there's no reason, in fact, to assume that they're always deterministic. So that begs the question, what happens in terms of all these approximations? What can we say if there's also randomness in the cost factor Q? And another perspective is, I've been saying time and again that, well, that makes the analysis a bit less elegant. This is also to show that indeed that's true. It will be less elegant than that we're used to. Okay, here we go. To make this as easy as possible, let's assume for the moment that the cost factor Q is the only random part. That is, the matrix T and the right-hand side vector H are deterministic. Okay, then what are we dealing with? Well, that value function is by definition the value function of this primal problem, and now we observe that the set of feasible solutions doesn't depend on omega. Okay, we can describe this feasible set, which of course does depend on x, includes non-negativities, in the usual way. And we can say, okay, what do we know about this feasible set? Well, our standard assumptions are that we have complete recourse, meaning that the set is non-empty for any x, because there exists a feasible solution, and it's sufficiently expensive, which means that it's bounded in a formal mathematical way described. Let's agree that that's the notion. It should be bounded. So like we did in the other setting looking at the dual, we can now say this primal feasible set has is bounded and non-empty polyhedral, so therefore it has finitely many extreme points. Depending on x, for fixed x, we can use that. Okay, let's call them y1 up to yl, depending on x. Then we know that our value function can also be described as this. V of x and omega for a given x, because that's what tells us what those extreme points are, can be written as the pointwise minimum of finitely many functions which are linear in Q of omega, that is linear in omega, by our assumption of dependence of Q of omega. In other words, it's not too difficult to see that the value function is actually concave in omega if omega appears in that cost vector Q, which is very different from what we saw when it was in either the matrix or the right hand side or both, because then it was convex in omega. Remember? So what does that tell us? In this particular setting where the randomness is only in the vector Q, Jensen tells us that since we're comparing, well, a concave function in either its expectation or the expectation of that function, Jensen tells us what we get by looking at the EV problem is actually an upper bound. So exactly the opposite of what we found in the other setting. I leave it to you to verify that this is actually correct. I could repeat everything we said over what does this mean for the latency approximation, for the expected value approximation, value of stochastic solution for the DPI, and so on. I won't. Of course, you can do that for yourself. Who thinks, yeah, that's a good idea. That's what I'm going to do. I can always trust that you're very honest. Okay. Quite another question is, okay, if we drop that assumption that randomness is only in the cost vector, and allow randomness in T and H as well, then things become difficult, right? Because the dependence on omega is for one part of the problem in a convex sense, and for another part it's concave. So the message is there's no way of using that. Final remark gets a star because it's very important. What we've been doing today, and we've been doing for a number of lectures already, is talk about optimal values and bounds and relating optimal values of various models. We never talk about how the corresponding solutions actually differ. Let's take two of those problems. The expected value problem, and we say its solution is XEV, versus the recourse problem, which is X star. Typically, they will not be the same. And the question is, what can you say about the differences of those vectors? Right? they have all some interpretation, and what you will see if you take a close look is indeed that looking at the solution X star of the recourse problem, it shows that it is the solution of such an advanced involved model, because it allows for options, keeping your options open and so on, whereas a deterministic solution, there's no such thing, there's no reason, because you already know the truth. So the suggestion is that if you look at an application, also look at those decisions, first stage decisions, looking at all the second stage decisions is what we ask you too much. But look at those vectors of decisions and try to say something meaningful about the differences you see. Can you understand why the differences are as they are? You get my point? Second part of today's lecture, as announced, is on a different but related subject. In fact, I'm now going to talk about what we call stochastic linear programming, approximations of distributions. So what is the setting? Typically, we're dealing with a problem that's given to us, and our assumption is we're also told what the distribution is. Of course, it's in practice very difficult to get it, but we are given it. In particular, if that distribution of that vector omega is continuous, we've seen that that brings all kinds of issues. Function evaluations, let alone gradients, subgradients, and so on, become very, very difficult. That's why it would be very helpful if we could do something smart. Namely, replace that given continuous distribution by a much easier distribution to work with. Preferably a finite discrete distribution with not too many mass points, not too many realizations, because then calculation of the expectations becomes really easy, right? And in doing so, we should keep in mind that our goal is to get indeed good approximations of what it is that we wish to learn from solving the recourse problem. That is, we want to get a good solution, so X star, and a good approximation of the corresponding objective value. That's what we aim for in this exercise of finding those approximate solutions. It's not that we're interested in approximating that particular distribution. Right? Well, at least those who are econometricians find that more natural. That's what you do all the time, and then maybe you say, okay, I call it a good approximation if the first so many moments agree, something like that. No, that's not what we're after. We are after precisely this. In the end, we want to have good solutions and good approximations of the corresponding optimal value. So any simple distribution, preferably a small one in the sense that I described, that does this job is very well. That's what we're looking for. All right? Let's see. Well, we don't start from scratch because we already know quite a few things. Like before, I'm going to assume that the randomness is only in the matrix T and the right-hand side. So from now on, view again as usually is the case is fixed, deterministic. Okay. And what do I know? Well, then I know that the dependence on omega of our function g, which is that sum of the first stage cost and the second stage cost, value function v in the second stage, is depending as a convex function on omega for any fixed x. So what I could say is, well, I'm interested in convex functions phi of omega, and there's actually a whole collection of those, namely for each x I get a different function phi, but in all cases it will be convex. So what I'm doing is say, okay, forget about the index x, I'm just interested in functions which are convex functions of some random parameter omega. That's what I'm dealing with, and of course all the time I have in the back of my mind that's actually g of x at omega or fixed x. phi that help us, I'm using this notation. Okay, what do we know? Well, for one thing, we know from Jensen that actually phi of mu is then a lower bound for the expectation of phi. Right? So my idea was that, well, I would be happy if I could construct a small size discrete distribution which gives me such an approximation. Well, here it is. I just replaced the random variable by the mean, and then Jensen tells me you get a lower bound. Well, that's a one-point discrete distribution. How easy can we get? So that part is already solved for now. We'll get back to it. So in terms of random variables, this is the statement that we arrive at. Namely, I define a new random variable, let's call it psi, and I define its distribution to be degenerate. Namely, with probability 1, it's equal to the mean mu of omega, the distribution of random variable that I started out with. And then, well, I have indeed a lower bound in terms of that new random variable psi. Its expectation is a lower bound for the expectation of that same function phi with respect to the difficult distribution omega. Or maybe it's continuous. Okay. So far, so good. The question is, of course, can we do a similar thing to arrive at an upper bound? It's a very natural answer, but the thing is that we have no choice. We're dealing with convex functions. Right? That phi is just a placeholder for the function we're actually interested in, g of x and omega. And we know, under our assumptions, that g for any fixed x is a convex function of omega. But you're right, if it were concave, we would be done. But it isn't. It could be both, right? If it's linear, but it isn't. Yeah. Anybody else?
Yeah, there
Check
was,
it.
I thought uniform because it's linear and
What do you mean by uniform?
well, I was thinking of constructing like a linear
Yeah.
distribution so that it's both convex and concave.
I'm not sure that, I think you're mixing things now. You're talking about a linear distribution. I'm not sure what you mean. But maybe, and you can tell me, if I show you a picture, maybe this is what you have in mind. Let's see. In fact, before I show you the picture, let's simplify a little bit. I'm going to talk about a scalar random variable only from now on, claiming that actually this can be generalized to higher dimensions, and in fact, we will later. Moreover, I'm going to assume that this scalar random variable has bounded support. So there is some finite a and b, such that all probability masses on that interval AB. Of course, if I have unbounded support, I can cut off the tails and tweak it a bit. Similar results, maybe not the same, are true for higher dimensions and for unbounded support. For now, this is the setting. Yeah? Okay. We do know that Jensen doesn't come out of space. It's based on the subgradient inequality, and this is the story. We have a convex function of phi, which is restricted to this interval AB. And if you take the expectation of the random variable over that interval, then maybe this is its mean value. And in that mean value, I can construct this supporting hyperplane with corresponding subgradient, vector u, not scalar in this case, which tells me that this linear function is a lower bound. And that's what I use and brings the result of Jensen. Namely, I write the subgradient inequality that we've seen already a couple of times, and I take the expectation, and what comes out is Jensen. Okay? And now I say, okay, what else do I know about convex functions? And the picture is already given away, and maybe Shane, that's what you had in mind. There's this dashed line. What is it? What does it stand for? Which property of convex functions is described by this picture. Yeah, so chord. Yeah. We do know, as a property of convex functions, that if you construct such a chord between 2 points that are on the function, that defines a linear function, a line, which is always on or above the graph. That is, it's an upper bound. In terms of convex sets, it says take any 2 points on the boundary, if you will, connect them, and that line will be inside the set, that is, inside the epigraph. That's also a known property of convex functions. And that actually does the job, as I will show you, namely, in terms of mathematics, this is what it is. I describe now the chord using the function values in the extreme points A and B. That's why I have to assume that it is bounded. Okay? The property that I just mentioned is that such a chord is always an upper bound on the interval AB, assuming that the function phi is convex, as is given. Okay, also for this inequality, I can take the expectation, and I find it convenient to just switch sides. So that's why the direction of the inequality changes. And this is what I get. Have a look at it, and convince yourself that's actually correct. Okay? Now, I'm going to play my standard trick. I'm going to take the expectation with respect to omega, and this is what I get. Barely visible, but I don't want to give away the next line. Okay. This is what we get. And I'm inviting you to tell me, to tell us, what it is that you observe. What are we looking at? It says, on the left-hand side, there is this difficult thing, the expectation with respect to omega, that nasty continuous distribution, difficult to evaluate. Well, we get an upper bound in terms of the expression that you see over here. What is it? What is the structure of that expression? Let me spell it out for you. There are two constants involved, phi of A and phi of B. And each of them is multiplied by some factor, which is not just something. Yeah. The weighted average, but not just by just any weights. What do you see about those weights? Mu is the mean value, which is in between B and A, right? So B minus mu, negative, as is B minus A, it's positive, and the same holds there. So apparently those weights are non-negative. How about the sum? Sum is 1. How do we call such weights? The probability. So actually, what we found using this other property of convex functions, namely that the chord is always an upper bound, gives us a very similar thing, but now specifying an upper bound. Whereas Jensen gave us this, well, degenerate distribution providing a lower bound, apparently what we now get is a 2-point distribution giving an upper bound. Wow. So to summarize, this is what we do in terms of random variables. We define a new random variable, I call it eta, and it has only 2 possible realizations, namely those 2 extreme points, A and B. And for each of them, I copied those weights that we just derived as the corresponding probabilities. And my result is that indeed to bound from above this difficult expectation with respect to this arbitrary continuous distribution of this convex function phi, I now have this upper bound in terms of that indeed easy distribution. 2-point discrete distribution of the random variable that we just named eta. That's almost too good to be true. Well, it is true. This result, using that corridor higher dimensional generalizations, is very famous in the stochastic programming literature. It comes under the name of Edmondson-Madansky inequality, and therefore the lower bounding distribution we might call the Jensen approximation, approximate distribution. This upper bounding distribution we would call the Edmondson-Madansky approximation. And since I'm lasing out, I'm not going to write Edmondson-Madansky in full all the time, so it will typically be EN approximation. Okay. The conclusion is this. I started out with an assumption on the distribution, which is quite flexible. Namely, the only thing I assume is that we are given a distribution for the random variable omega, which has mean value mu, and it has support this bounded interval AB. For any such distribution, and for every convex function phi, my only assumption is that it's convex, finite value convex, is sufficient to give me this, both a lower bound as well as an upper bound, in terms of those very easy, small, discrete distributions that I was looking for. Namely, the Jensen approximation, and this picture tries to capture what it does. It says, okay, take all the probability mass, which is 1 on this interval, and put it on the mean value. In the same picture, you have EM, stands for Edmondson-Madansky. It does a similar thing, but different in the sense that it takes the same probability mass, and according to some formula, puts it on the extreme points, A and B. Both define then a distribution, 1-point, 2-point distribution, and we do know that we have this inequality. The Jensen approximation gives lower bound, the Edmondson-Madansky approximation gives upper bound. And it's true for any distribution that I started out with, and for any complex function. So in particular, function g of x and omega for any fixed x. The one we're interested in. All right, so that's the good news. Here's the bad news. This is a very general result, and in fact it's not difficult to show that these are the best bounds you can get, because the set of distributions I'm considering actually includes the distribution of psi as well as the distribution of eta. So it's sharp in that sense. They are the best bounds for this very general setup. But of course that doesn't mean that for the particular function that we are interested in, namely g of x and omega, the bounds are actually any good. We know for sure there will be a lower bound and an upper bound respectively, but the gap will be way too large for any practical purpose. You see the issue. So here's the question, what do we do? You can be very disappointed and look for something else. That's not all right. Or better than that. We'll give up. This is a way of an exception. Any suggestions? How about this? Refine the approximation. Our approach so far led to a lower bounding distribution on 1 point and an upper bounding distribution on 2. That's indeed very true. So if we can apply the same ideas but yielding refined approximations, so a lower bound maybe not on one but on a few, and an upper bound not on two but a few more. If we can do that, it's reasonable to hope that the corresponding approximations will actually become better. That is, the gap between upper bound and lower bound is smaller. And here's how we could do that. The idea is to say, okay, I'm given this bounded support, that capital omega, and I'm going to partition that support. I'm going to divide it in subsets, such that together those subsets actually cover the support, and there is no overlap, that's a partition. And I'm going to apply essentially the same idea to each of those subsets. That is, I'm going to apply the Jensen approximation and the Edmonds-Podolsky approximation on the subset. And that's not a very strange idea. Actually, we're allowed to do it. Because, okay, here we go. I take this interval AB and I subdivide it in a finite number of subsets. And in the example it's just 2. Yeah, I call them omega 1 and omega 2. And here's the boundary, I call it S1. And on each of them, of those subsets, omega k, I'm going to calculate the corresponding probability mass, which I can do. And for each of those subsets, I'm going to calculate the corresponding conditional mean value. Given that I consider only that subset, what is the mean? According to the distribution of omega is given. That's what it spells out over here. And then I observe, okay, on each of those subsets, I can consider the conditional probability of omega being no larger than t, given that I'm on the subset, and I observe that that's actually a distribution that corresponds to a function. That holds for each and every one of those 2 in the example subsets. And in fact, to calculate the expectation of phi, I can use conditioning, that is, calculate that expectation according to this formula, which says, well, to do so, I can do that component-wise by considering just such a subset that is conditional on being in the set omega k. All right. Putting this together tells me that on each of those subsets, I can actually apply Jensen and Edmonds-Podolsky. And here it is. On each of those sets omega k, I apply very much the same trick. I take the probability mass on that subset, and my Jensen approximation for that particular subset will be to put that probability mass on the conditional mean. That's the Jensen arrow over here. Edmonds-Podolsky does, like before, a similar thing, except that it takes the same probability mass, but instead of putting it on the mean, it puts it on the extreme points according to that formula that we've already seen a couple of times. Now, mind you, since we're looking at neighboring subsets, in fact, such a boundary point Sk will get probability mass from 2 sides in the Edmonds-Podolsky approximation. That's why we get the following result. If I start out with a partition in capital K subsets, then my Jensen approximation will be on k points, namely on the k conditional means, uk. And that then defines my lower bounding distribution. On the other hand, I can also, using the same partition, find an upper bounding distribution of Edmonds-Podolsky type, and if you see the picture before your mind, then actually that will get k plus 1 points, because of, well, those boundary points getting probabilities from the side. Okay. By the way, this is not an h, this is a capital eta. Right. So this is what we get. apart from the technicalities, exactly the same thing as we did before. We constructed a small, meaning with a few realizations, small distribution, discrete, that provides a lower bound. And same thing, using Edmonds-Wodanski, again yielding a small discrete distribution given the upper bound. The theoretical result is that if you keep refining the partition, the gap between the upper bound and the lower bound doesn't become larger. That's somewhat disappointing. We were hoping that we would get a guarantee that it gets better. In practice it does. I'll show you an example in the next slide. Final remark is this. It's interesting to analyze the same ideas, but now apply to a problem where randomness is also in the cost vector. And assuming that there is sufficient independence of things, very speaking, if you get my meaning, you can actually conclude that, okay, if you apply the Edmonds-Wodanski approximation to those cost vector components, and at the same time the Jensen approximation for G and H, what you get is a lower bound. Similar statements can be constructed, and that's my invitation to you, to at least think about it and try to make sure that you understand how things are working. Yeah? Final slide for today is to show you an example of such a approximation of distributions. Here's the first picture. And let me tell you that what you're looking at is the expected value function of a simple recourse model. So we have unit penalty cost for surpluses and shortages. And the slope here is -1, and the slope over there is +3. And my question to you is, what type of, and okay, what are you looking at? Well, this smooth curve is that particular simple recourse expected value function. And this purple line is the very rough Edmonds-Wodanski approximation. And this blue one is the Jensen approximation. But my first question to you is, okay, given that this is the recourse function and these are the asymptotes of that recourse function as we know it, can you tell me what the given distribution of omega is? So which distribution do we start out with? Again, I've been playing around with these functions so much, using the software and so on. Let's break it in part. What is the support of that random variable? What can you use from your knowledge? For example, we do know that outside the support, to the left and to the right, that recourse function actually coincides with the asymptotes. Remember? Okay. Apparently, that happens to the left of 0 and to the right of 4. So the support apparently is 0, 4. The other observation, but that's asking too much, is that this is indeed a smooth function, so the distribution is continuous, and in fact it's a uniform distribution on 0, 4. Okay. And now I play the game that we just introduced, namely constructing a Jensen approximation and an Edmonds-Wodanski approximation, and I'm going to iteratively refine that approximation. So the first is constructed using the full support 0, 4, and well, do what it takes, namely calculate the mean for that support given the uniform distribution, which is 2. So my Jensen approximation will have a single mass point, and that's here. The Edmonds-Wodanski approximation will be on the extreme points, so 0 and 4. And who can tell me what the corresponding probabilities are? A half and a half. That follows immediately from the formulas. Okay. We probably all agree that this is a lousy approximation. want to optimize this function, and instead we consider those piecewise linear upper and lower bounds, and they are no good at all. So indeed, we're going to improve by considering two subsets, namely 0, 2 and 2, 4. And on each of them, I calculate the corresponding conditional means, which are 1 and 3, so they are the mass points in my Jensen approximation. And for the Edmondson-Madansky support, I get, well, the extreme points of the interval 0, 2 and 2, 4, which is 0, 2 and 4. And again, the corresponding probabilities are easy to calculate. For the Jensen, it's a half. For Edmondson-Madansky, what is it? 3 points.
Quarter.
Yeah, very good. Actually, this point 2 gets a quarter from this side and this side together. Okay, are we happy? Not quite. Let's refine again. Now, I'm using a partition in 4 subsets. And on each of them, I calculate the corresponding Jensen and Edmondson-Madansky approximations, and I gather everything, and this is what it brings. And definitely from the back row, that looks like a good approximation. So, yes, it pays to do a little bit more work. The message is, this approach, constructing discrete approximating distributions, is a good way to obtain reasonable approximations, but do not expect miracles. And we need to spend some effort to get decent approximations, but it's doable, at least in low dimensions. How about larger dimensions is a subject for the next time. Okay? I'm 6 seconds late, so time to stop. And you need to go to the master seminar. Right? Okay, see you tomorrow. Ja.